Hello. Today we will continue to learn to find the transfer function for electromechanical system. We will see some more examples. Let us practice this example. You can see that we have a gear here, actually double gear, one from, for example, N1, N2, N3, N4. Okay, so at first we have to have a clear idea about this gear. If we want to move this inertia from the left side to the right side, we have to multiply with two ratio. One is N2 by N1, which is 20 by 10. Another is N4 by N3, which is 60 by 30. So you might make a mistake, which is you might use 30 by 60 like this. Okay, so you have to make sure that you are just remember that we are moving this inertia from N1 to N2 and then N3 to N4. So use the inertia properly, ratio properly. Okay, and then we can see that there is a combination of rotational and translational gear here. So if we rotate this gear, rotational gear, cylindrical shape, then if this gear moves, the translational gear also moves in along the vertical direction like this. It is called 1:1 gear. It means that if 3 teeth of this gear moves, there will be movement of 3 teeth along the vertical gear. Okay, translational gear. So this means 1:1. So and we also need to know that there is a direct relation between this rotational variable theta and translational variable x. And what is the relation? Relation is x equal to r theta. This is from the geometry. Okay, so let's talk about the number of variables. We can see that there will be a theta here, theta dash, we just name it theta dash, and this is theta, and there are no more theta here, and this theta is 0. Okay, and with this theta there is a coupling with translational variable x, but this x is dependent on theta. You can write x equal to r theta. R is the radius of this cylindrical shape gear, the radius, inner radius, which is 2 meter. Okay, and also this theta is dependent on this theta dash because there is a coupling through the gear. Okay, so we can see that this theta dash, this theta and this x, they are all dependent on each other. So the number of independent variable is just 1 because all of these three depend on each other. So there is only one independent variable, and we are going to write only one equation. At first, make it clear. Okay, if it is clear, then we have to choose where we are going to write the equation. Is it on the left side, or is it on the right side here, or is it on based on x? We can write the equation any of these three places. Okay, just any one place. So we will choose in the middle because it is convenient to shift the stuffs from here to here and shift this translational component to the middle part. So it is more convenient. If we choose, for example, theta dash, we have to move these parts all the way to the left side of the gear. Okay, so that is rather complicated. So we are going to write the equation based on theta. And also you note that I did not write here like theta 1, theta 2. I did not write it like that because I wanted to you understand that these two theta are dependent. So I write it like in this fashion, that one is theta and another is theta dash, to indicate that these two are basically same, are dependent variable. Okay, so next we are going to write the equation. So if we write the equation based on theta, we need to include all the impedance here. So what are the impedance? First of all, there is the impedance inertia, which is the weight of this heavy gear, which is 3 kg meter square. Okay, so we have to include this 3 here, but we also need to transfer this 3 kg from the left side of the gear to the right side. Okay, so we have to transfer it, and to transfer it we have to multiply with some gear ratio, right? And what is the ratio? We have talked about it, that is 20 by 10, 60 by 30. Okay, because we are moving from 10 to 20 and then 30 to 60, right? So use it properly. You need to fill this up. Similarly, there is a d2 which is not exactly based on theta dash, which is actually in this axis, so we need to transfer this d2 only by multiplying this ratio, that is 60 divided by 30. Okay, only one ratio, not two. So use it here, and I will also need to add this, that is 1. Actually this should be 1, not 2. So please make a correction here. And then we have no other spring or anything else. Then what we have is this one. Okay, this is translational part. So I write this. You need to understand there is a coupling between this translational part and this rotational part. And this rotational part, for this rotational part we are writing an equation of torque. You see on the left side there is a torque T, which is applied here, but we also need to transfer this torque from the left side of the gear to the right side. Okay, so we also have to multiply with a gear ratio. This is a double gear ratio, that is N2 by N1 and N4 by N3, something like that. Okay, so so use it here. So what you need to clear is to make understanding of this translational part. Okay, I'm explaining that now. So for this translational part, you need to understand that you are writing the equation for torque. This is a torque equation, and in the translational component there is no torque, there is only force, right? So there are all of these are force component, and I have written down all of these component together with single notation, that is F. I have written a simplified version of this. And this force, for example, all of these force component are combined into F, and now we need to convert this force into the rotational torque equation by multiplying with R. So we need to remember this relation, that torque is equal to force into radius. Okay, and the radius is what? Radius is this radius of this gear, because this force is working on the periphery of this rotational gear, and if it is multiplied with the radius r, then we will get the induced torque in this theta. Okay, so this is the basic equation. Now we need to write details, the component of F. So here we see that we just written down the theta into all the associated impedance, and then there is a translational part. We write it in simplified from F into R. because if we multiply force with R, then we get the torque. So this torque should be included in this equation of theta, okay, is equal to the applied torque, which is T, and T should be transferred from left side to right side by multiplying proper ratio. Now what is inside F? The F is nothing but is equal to X into the impedance associated with here with X, which is 2s square, which is the mass, and then 2s this for disc damper, and plus 3 for spring, etc. So this is the value of X. So you need to put this value in here, okay. So replace this F with this expression in next line, and then what you need to know is another equation just like this one, rotational and translational relation. Torque is equal to F into R. There is another relation between X between X and theta, which is X is equal to R theta, okay. So if we multiply R with theta, theta with R, we will get X, okay. So you need to remember this relation, because you have to find either the transfer function X divided by T, or you have to find the transfer function theta divided by T, any one. So for example, if we want to find the transfer function X by T, then this equation should be converted into X by replacing this theta by X, okay. We have to replace the theta with X, so use this relation to replace this theta into X, and we already have X inside this F, right? So you convert you rewrite this equation in terms of X, or to find the theta by T transfer function, you have to convert this X into theta, which is appearing inside the F, right? Inside the F there is X, so you have to convert this X into the theta by this relation. So once you convert this left side of the equation either into X or into theta, you can easily write the transfer function, okay. So that's all for this example. If you properly understand this, then you can move on to the next example. So let's talk about this. The main difference between this example and the previous one is that the number of variables, look at the number of variables. How many variables are there? Can you pinpoint it? I will give you a few seconds to think about it. Think about it. How many variables are there? There is no gear. One, two, or three. How many variables? Or four? Don't remember there is a spring in between this inertia. There is a viscous damper in between these two inertia, okay. So if you consider it properly, we will find that there are three rotational displacement, because there should be different variables on both sides of the spring and damper, okay. So there should be a theta 1 here, theta 2 here, and theta 3 here. And there is another translational variable just like previous example, X, but this X is dependent on theta 2. So because this is dependent, so these three should be the independent variable. So number of variables in total are 3, and this we will going to write 3 equations. Now let's have a look. At first we will write equation based on theta 1. So we will write the impedance connected to theta 1, which is J1 and K1, we'll write these two component here, and then there are common parts or impedance in between theta 1 and theta 2, which is k1. So we'll write it here because we are writing the equation here based on theta 1. So the common part will appear in between theta 1 and theta 2 along with theta 2. So the k1 should appear here, but there is a no sharing impedance between theta 1 and theta 3, so there should be nothing, should be the 0 here, and the t should appear on the right side. So this is the equation number 1. Now let's write down the equation number 2, which is critical here, just like previous example. In equation number 2, we are going to write equation based on variable theta 2, and it should be here minus theta 1 into k1, because k1 is appearing in between theta 1 and theta 2, and then theta 2 is associated with 3 direct impedance. One is J2, another is G3, and another is K1. You should write it here properly. And then there is extra part, translational part, F into R. This part, because this part is directly connected to theta 2 through a translational 1:1 gear, coupling gear, translational to rotational. So this F into R part should appear directly with theta 2 and with the sign plus. This is not minus, okay, this should be plus. So this is the direct part of theta 2. So there is a direct relation between theta 2 and x. There is these two are dependent, so they should appear as a single unit. Okay, so just like previous example, this term should be included, F into R, and then minus theta 3, just like our previous example, previous lectures. Theta 3 should be accompanied with D3, because D3 is the common sharing component in between theta 2 and theta 3, okay, is equal to 0, because there is no torque, external torque applying here, okay. And then we can see that the third equation we can write down in similar fashion. This should be 0, this should be D3, and this should be J3 and D3 equal to 0, because there is no torque. That's it. So these are the 3 equations that should be written for this example, but don't forget that there is a component F which is equal to this one, okay, and there is a relation between x and theta 2, because you might need to convert the equation for transfer function x by t. In that case, you have to first solve theta 2, and then you have to, for example, you can solve theta 2 here from these 3 equations using Cramer's rule, and then convert theta 2 into x by this relation, okay, then you can find x by t. And if you need to find any of this theta by t, it can be theta 2, it can be theta 3, anything you can find directly from these equations, okay. So that's all for this example. I hope you understand. So you can see that in our previous example there was only one variable, but here there are 3 variables, so this is rather complicated to solve the transfer function, okay. Let's go to the, if you understand it properly, please, if you don't understand, write the equations by yourself, take your time, and then move to the next slide. Now let's talk about this example. How many variables are there? I will give you a few seconds. What I mean is independent variables. How many independent variables should be here? You can see lots of gear here, right? So think about it, how many? The answer is 2, because we can see theta 1 here, but this theta 1 is dependent on theta 1 dash, and this theta 1 is dependent on theta 1 double dash. Okay, so we have to understand that from here to here there is only one independent variable, and there is another variable on this side which is theta 6, and there is no theta here because it is 0. So there are only two variables, one is theta 6, another is, for example, theta 1 double dash, etc. So we have to write only two equations in this case. Okay, but don't forget, when you are writing this equation based on theta 1 double dash, then you need to find properly the impedance. Okay, for example, you have to transfer this J1 and D, which is connected to theta. You should transfer it twice, once by multiplying n2 by n1 square, and then multiplying n4 by n3 square. Okay, and there is another inertia and damper J2D, and there is another J3 here. Okay, and there is also here J4 and D, and there is J5. So lots of impedance component are here which should be included with in this part of the equation. And in between theta 6 and theta 1 there are two components which is D and K2 should appear here and here. And in theta 6 you can, I think all of you can write this part, which is this J6, D, K2 and D. Okay, this should be appearing here. So I think you are familiar with the rest of the style. This is not applicable here. So in our next example, let's see another example where we have the coupling rotational with the translational, but we also have a motor here. So this is the electromechanical system with rotational translational coupling, and we have given all the parameters for the motors. So at first we need to understand how many variables are here. I will give you a few seconds. So the answer is only one independent variable. How? Let's see. But first of all, this theta dash and this theta is mutually dependent. Okay, and this theta is applicable from here all the way to here. This is all the region of theta, and then with this theta the translational variable x is dependent on. Okay, so all these three variables are dependent, mutually dependent. So there should be only one independent variable and one equations only. So we are writing the equations once again in the middle part, just like this. Now let's have a look. So with this theta there is a inertia which is this one, J equal to 1 kg meter square. Okay, and there is another inertia connected with the motor which is JA 1 kg. So you need to move that. Okay, you need to move this JA from the left side of the gear to the right side. Okay, so these are the two inertia, and then again similarly we have a viscous damper D, and there is another damper on the motor side which is DA, who need to be transferred by multiplying a ratio. And then we have a translational part which is plus F into R. Okay, theta into impedance plus F into R. So you need to include it just like our previous example. And then equal to Tm into something, because the Tm is the developed torque on the left side of the gear. Okay, so Tm is developing here, over here with the motor, which is left side of the gear. We need to transfer it to the right side by multiplying the gear ratio N2 by N1 whole square. And now you need to understand that our input in this system is not Tm. Our input is electrical here, which is EA. So you need to convert this Tm into EA by using our formula, which is shown in the slides of DC motor, which is this one, right? So you need to use this formula to replace the Tm to get the EA. Now what you get is a big equation. Here we can see that the theta dash is appearing, because theta dash is connected to the motor, which is actually theta m in our original equation. So this theta should not appear on the right side of the equation. Rather, this we should convert this theta dash into theta, and then we should move it to the left side of the equation. Okay, and then you can finally get a single equation of theta, or you can convert the theta into the x by using our previous relation, x is equal to r theta, and then you can find single equation either in terms of theta or in terms of x. Okay, so the only new things in this example is this one, to convert Tm into EA, but we have to we should note that there is a additional term of theta associated with this part. So this theta should be transferred to the left side of the equation and combined here with this theta. Okay, but before that you need to convert theta dash into theta, and if necessary theta into x, or you can also convert the equation in terms of theta if we convert the x inside the f into theta. Okay, so the final transfer function can be x by EA or theta by EA.